Before we get started, does anyone have any questions about access to any of the materials on Moodle or other questions? I've got the assignment that's due today that we can go over at the end of class if there's any questions for that. But if there's any logistics stuff, is anyone having any problems with textbook or email or video access? Oh, okay. Everybody seems to be ready. Let's see. Someone wants. Where is? I have them. Okay, you guys are all doing great with the video stuff. I'm the one that's having a hard time. All right, I've got participants. There he is. Okay, I have to wait for it to like pop up to show me. All right. Jesus, welcome. Anyone else? Waiting, can't see anyone. Okay, so we are going to continue. Did I start this? I did. Okay, we're going to continue today with a little bit more detail on passive systems. A little bit more in line with a couple of the methods that the book breaks it down. Now, keep in mind, that's one approach. It's a pretty good one. I think this is an excellent textbook. My approach is a little bit different, but they have a lot of really good material in there. And so the stuff that I'm including is going to focus on the parts out of the chapter that I think are most relevant for you as designers moving forward. And it's not necessary, they categorize 3 different types of passive heating with the direct gain, the trom wall, and the sun space. But I think the 2 most important ones are the direct gain, which is basically a traditional passive heating system, and then the trom wall, which is applicable in so many different ways. I find their definition on the sunroom is a little less applicable. So, starting with the direct gain design guidelines, again, this is like what's considered the traditional passive solar heating. It's where you have got your glazing, you have your sun coming in, it's hitting your thermal mass, and it's re-radiating heat out to the space. From last Monday, there's the 5 different components of the system: the absorber or the collector, which is the glazing, the control, the thermal mass, the absorber, which oftentimes is the same thing as the mass. So there's a really, really bad picture in the textbook of this project. The photos I have they're not super clear, but this project is the Real Goods building, Real Goods Solar Earth building in Northern California. I believe it's pretty far north, almost to Oregon. I want to say it's Redding. I can't swear to that's the right city name. This one's been around for a while. It's about 20 years old. It's a pretty good building, really good design. It's a commercial space. It's a retail, but it's also on this land. The Real Goods Solar Earth Goods book, whatever, is a catalog from the 60s. It's still around. They're a retail chain and catalog that sells solar and eco-friendly products. It's designed in sort of a circular fashion, facing south, big overhangs, lots of gardens around it. But one of the things I find most interesting about this project is that the architect for it is Sim Vanderen, who has been a practicing architect in the state of California since the 60s. He was actually the state architect when Jerry Brown was governor the first time back in the 70s. And he is the person that established the energy performance codes for California. So when you guys are working on Title 24 calculations or working with your engineers on that, Sim Vanderen, who's still practicing up in Marin, just north of San Francisco, he is the architect that you get to thank for establishing that system. So this is this project is just a traditional passive solar heating project, and it's the climate there is fairly northern for, I mean, utmost northern for California, so they get a wider range of temperatures than we do down here in Southern California. Climate is a big factor. Climate, latitude, and solar hours are a big factor for designing a passive solar heating system. This is a chart that has it's straight out of the textbook. It's mostly kind of rule of thumb to help gauge how much south-facing glazing you need for different types of climates and locations. So this is the, whoops, see, that's not what I wanted to do. I wanted a circle. This is the amount of glazing area, that's a percentage of your floor area given a different climate. So you'll notice a very far northern climate, such as Madison, you need 40% of your floor area in order to have a passive solar heating system, versus Los Angeles, which is what we can consider San Diego to be. We can do the same amount of heating with just 9%. And that is to reflect the heating load that is so much greater in Wisconsin than it is in San Diego. And Florida is even less. This also is a guide to help you think about the relative importance of what the heating load is on a space. So in Florida, Miami, which is southern Florida, you can have passive solar heating with just 2% of your floor area being glazing. So that is an indicator that heating is not a main concern in that location. 40% in Wisconsin, heating is a big concern for the design of buildings there. The two far right columns are comparing with night insulation and without night insulation. This is most likely going to be the person inhabiting the space having to actually actively be involved in making this system work. Night insulation can be as simple as pulling the curtains closed in front of the glazing. And the goal of the insulation is all that heat that has come in during daylight hours through the glazing, hitting the thermal mass. You want to keep that heat in the space during nighttime to re-radiate into the space and not losing it back out through the glazing. So it's inhabitant activity that has to be part of the system. And like I said, it can be as simple as shutting the curtains. It could be a pair of shutters. They actually, I mean, getting solar shades on mechanical shades with new low voltage controls and stuff. Not that complicated anymore. Lutron has some really good systems, but it's important to keep in mind that it's not a design it and let it go and it's going to work all day long, all night long. It's participation involved system. Okay, so this next chart, which is also directly out of the textbook, the most important column here is this column, the surface area to glazing area ratio. So a ratio being how much glazing area do you have to, or surface area do you have to the amount of glazing that you have. So for masonry or concrete, it's a 3-to-1, 3 being the surface area of your thermal collector, 1 being your glazing. Or if you were going to reverse it and say glazing to thermal mass, it would be 1-to-3. Essentially, you need 3 times the amount of square footage of your thermal mass. This is not cubic feet, but just square feet compared to your square footage of your glazing area. This is masonry or concrete that is exposed to direct gain. That's where the sunlight's coming straight through the glass and hitting the surface. If you're collecting it from a reflected surface, say the solar gain's hitting the floor, a light colored floor, white colored floor, and reflecting to another wall surface or another plane, you need to double it. So your ratio would be 6-to-1. Water, an excellent thermal mass, but you can't have water on your floor. Well, I suppose you could, but it's an unusual floor surface. It could be a wall surface, but you need a lot less water area, half of your glazing area for absorbing your direct solar radiation. Water works much better in a trom wall situation, and we'll be getting to that. Phase change material, we briefly talked about that on Tuesday. If it's in the path of direct solar radiation, it's a 1-to-1 ratio. So there's a great example in the book here, and I want to walk you guys through it. Okay, so this is the example straight out of the book, and so we have a very straightforward building. It's 1,000 square feet, 50 feet running east-west, 20 feet running north-south. My little circles. This, it's not overly clear, but the arrow is the direction of the sun. Okay, quick little section over here. In this instance, the floor is the thermal mass. Okay, so how do we start sizing this or designing this system? The given situation for this example is in Little Rock, Arkansas, and I typed AZ instead of AK, sorry, wrong state initials there. Let's just go with Little Rock. So we go back to our chart with our different climate conditions, and Little Rock, Arkansas, rule of thumb guidance is 19% of your floor area is needed for a direct gain passive heating system. So 19% glazing. And again, this is a percentage of the floor area. So it's based on the total square footage of the building, the room, whatever your design is. Okay, so 1,000 square feet at 19% is 190 square feet of glazing directly facing south. With this size, if you have nighttime curtains or shades or a method to prevent the heating from being lost back out to the exterior, you can expect that at this size, you can cover 62% of your heating load with passive solar. If you do not have that insulation at nighttime, as in during non-sun hours, it goes down to about 38%, so about 2/3 the ability. So again, insulation is key in performance. So we've looked at how much glazing we need. So what's the next step? We need to figure out how much mass we need. So this is the second chart we were looking at. This is where, if we're going to go with a masonry floor, we have a 3-to-1 ratio. So for every 1 square foot of glazing area, we need 3 square feet of floor area. And that's for concrete, specific to concrete. Sorry, I forgot to mention that. It's based on your material. Again, concrete, masonry, stone tile, these are all going to be about the same. And this is with this direct, with the sun hitting the floor directly as opposed to reflected surface. So with concrete, we have 3-to-1. And therefore we're going to need, and this is minimum. This chart is a guideline for the minimum amount of floor area that you're going to need. So we're looking at 570 square feet. So what's going to happen with that extra 430 square feet out of your 1,000 square foot space? Well, it gives you some design flexibility. In addition, it can also be if you've got large pieces of furniture covering up some of the floor area, and so it's not being active thermal mass, or you want to use an area rug. You're never going to have in a space, it's highly unlikely you will ever have a room without anything in it, except possibly like a yoga studio. That's one thing I could think of. But keep in mind that the 3-to-1 ratio, it's a guideline for minimum. The extra square footage is just going to help enhance the performance. By the more mass that you have, it's going to just make it a little bit more steady and take the extreme swings out of the curve. So it is not at all harmful. Okay, how are you guys doing? Are you following along with the ratios there and how you start trying to design for this space? Any questions so far? Okay, I'm trying to break it down so that you look at each part in sequence, one at a time. So first you look at your glazing, then you look at your floor surface area, and you have to make a decision on what your material is going to be. Okay, the next example, again, straight out of the book, is starting to look at a trom wall design. Okay, So the same rule of thumb guidelines for amount of glazing area needed based on location. So this location is, these percentages are an indication of how much glazing you need based on the latitude, which is going to determine the sun angle and the number of sun hours. As you remember from our solar geometry, the farther north you are in the winter, the less sun hours you have. Think of Alaska, think of the North Pole, think of the Arctic Circle, where in the dead of winter, you have practically no sun hours the farther north you go. So Wisconsin, your daylight hours are going to be that much smaller, which is why you need that much more glazing area during the winter to create your passive heating system. So we're still working in Little Rock, Arkansas, still looking for about a 19% percentage of our floor area for a trom wall design. In this case, as you recall, the trom wall is your glazing and your mass, both facing south with your airspace in between. Your mass square footage is always going to be a 1-to-1 ratio with your glazing, because you want all that energy that's coming through that glazing to hit your mass and have it all absorbed into that thermal mass. That's the basic part of how the trom wall works. So climate-wise, same glazing area, but the ratio of square footage of glazing to mass is always going to be 1-to-1. So we're still looking for 190 square feet of glazing area. Now, that thermal mass is going to be in a vertical orientation. I should add this to our little diagram here. So here's where our mass is going to be. Oops, I did that wrong. Undo. You can make it bigger than your glazing area, but you do not need to. But you do want it to be at least the same size. In this case, your thickness of material is a key factor for this type of system. In the Rhett Gain system, the thickness was not as key. Oh, well, that doesn't help to show that there. In the direct gain system, sorry, it's the same exact diagram for the two. You're only looking at surface area, but in the trom wall, you're also looking at thickness, because it's going to take a certain amount of time for that heat gain to travel through the wall and radiate into your space. So that's what this chart is showing for a few common materials. For adobe or dry earth, which is a clay dirt type, fairly solid material, 6 to 10 inches. Concrete or brick has more air bubbles inside. And as you know, or you remember, as I'm sure you all do, air is the #1 insulator. So when you have those little tiny air bubbles, it is going to affect the performance of your concrete or your brick. So you need a little bit more thickness for that, that material, 10 to 16 inches. And then for water, and trom wall is a great place where if you want to use water for thermal mass, you need 8 inches. And again, remember that ratio is always going to be 1-to-1 for area. but the thickness is going to vary based on the material. Now, if we don't need to get into it at this level of design, these are good rules of thumb. The actual thickness of your material in a trom wall, though, if you were going to do it, work with an engineer and work with your local climate to find out exactly, or do a little bit more further thinking that your thickness is going to be dependent on your sunlight hours. So you need to start looking a little bit deeper about the specific nature of the material to do a precise calculation. So again, these are just for the trom wall. For the thickness, you always are going to need a thickness, but it's going to also have some variation dependent on where you're located and what your sun hours are. Now, it's a balancing factor too. So for this example, we're working in Little Rock, Arkansas, where the guideline is 19% of glazing area per floor area. That's going to get you 75% of the way there. And then if you really want to dial it in, the next step in the engineering phase would be to work with that material, work with that exact climate and say, okay, I've got this much area, I've got what's my optimum thickness. But you can't go wrong with the range that the textbook is promoting here. It's really dependent on that, how precise you want to make it. And passive systems have a lot of leeway on either side, which is tied into also that leeway on thermal comfort. That's one of the things we were talking about on Tuesday, is when we are working with natural systems based on convection and conduction, we need to open our, we're not doing 100% mechanically heated or cool all time. And so the comfort ranges of that thermal comfort section can start to grow into the shoulders a little bit. But for the purposes of what we're learning at this level, rule of thumb and guidelines based on these charts from the book will get you there, 75, 80% of the way. So sometimes, and oftentimes, you're never going to have the ideal situation with an exact due facing south situation with the exact ideal geometry for a full trom wall. So you can, it's very easy, and it's fairly common to see hybrid systems where you're starting to combine some direct gain combined with some trom wall, and and so the second half of this example is looking at how to calculate that and design for that, where you're trying to mix different systems. Pretty straightforward. It's kind of like just cutting it in half. You want to take that, again, we're staying the same location, Little Rock, Arkansas. You want to take that 19% recommendation, split it in half. We're going to do half trom wall, we're going to do half direct gain, and then size your pieces of that two system 50-50, or you can do 25-75 or 80-20, 60-40. Just comes down to the math. So if you're doing half trom wall, half direct gain, take half of your recommended solar glazing area with a 1-to-1 mass, put in your material, concrete, water, stone, has your thickness, and that will provide half of your, or it's working to meet half of your space heating needs. The other half is your direct gain. So it's going to be your direct solar gain coming through your glazing, hitting your thermal mass, be it the floor or reflected get rid of that little rectangle here. And in this case, your floor slab area can go down because you're only using half of the direct gain. So if you have more furniture, you have more stuff in this space, and you have less floor area that's free to use for thermal mass, adding in a partial trom wall could really help your system perform better. Key thing to remember though is that trom wall is going to act like a radiator in the winter, and it's going to absorb the heat. The heat's going to travel through the material, through conductance, and then it's going to radiate out to the space and create convection to help heat the air and circulate the air around. Because this is a radiator, you don't want to block it with furniture or build it into a built-in cabinet or desk or something, because that will prevent that heat from being radiated into the space. A really nice example of a system like this is this project here. This is the Blue Ridge Parkway Visitor Center just outside of Asheville. It's a cool building. I haven't been there in person, but the photos are really awesome. This is one of the ones in the textbook too. Now let me get rid of this. Okay. The wall where they wanted to have the passive system was not, didn't have ideal orientation. And so what they did was they split it with this dual system that's, oops, undo. Half trom wall for afternoon, half direct gain for the morning, being absorbed in the slab. And I believe this is a 2-story structure here. So this is acting on both levels. They have some other stuff going on here too. And you'll find that is pretty common when a firm or a designer or an architect is trying to do or working on a sustainable project. They're not going to just take one system. They're going to combine a bunch of different methods together. And this project, this is one reason why this project is kind of cool, is there is also some clerestory windows up here. You can't really see them in this photograph here, but you can see this light shelf here is helping. So the sunlight hits the light shelf, it's going to help bounce the daylight into the interior of the space for daylighting to get lighting more into the interior. It's also got this super cool green roof going on, which this is a nice photo because it's after the roof has settled in a little bit. I've always been a huge fan of green roofs. We will lightly touch base on those this semester, but we won't really have a big focus on them. If you want to know more, let me know. I've got lots of resources. But one of the cool things about a green roof is it's also a fairly large thermal mass, but it's a cool one. So it creates insulation to prevent heat gain through the roof, but it also cools down the exterior. So in a super hot climate, it can be providing transpiration to the surrounding area. Speaking of which, I'm going to make a note. There's a really awesome project in Brooklyn. I forget the name of the architect off the top of my head, but it's part of the zoo, and it has a really cool green roof that becomes, It kind of melds into with the pathways through the zoo. It's really nice. So super cool example of a combination tram wall and direct gain system. It's another project that I wanted to show you. That is the Zion National Park Visitor Center. Again, another sustainable project with multiple systems going on. The tram wall on the south is just one of the systems. And we will be looking at this building again next week when we are looking more at some ventilation systems, and they have a evaporative cooling tower as part of their design. They also have clerestory daylighting going on, some more ventilation with windows, south-facing active solar, and then this wall here with a little bit of direct gain, and probably more for daylighting than direct gain with a clerestory window in the space. So that's the section through the building. In the photo, this is that tram wall here where it's appearing really dark. You can see the clerestory windows right over that, the operable windows in the upper clerestory here, and then you got your passive or your active solar panels here. A lot of stuff going on. It's not a very large building either. Definitely pretty cool. I like a lot of the sloping of the roof. This is a pretty severe roof pitch, but I love this photo here where it's starting to relate to the natural landscaping going on around it, the background. This project won an AIA Top 10 Coat Award, which is Committee on the Environment. I want to say 5 or 6 years ago now. I can't remember exactly which year it was. The years just keep going by. But the Coat Awards from the AIA are always really fun to pay attention to. They show you what the latest and greatest sustainable projects out there, what kinds of stuff that they're doing. Okay, so 2 really cool examples of some contemporary passive systems. Any questions before I move on?
Yes, I have a question about the green roof. Is it expensive than the regular roof, or not? Like,
Is it
expensive? Yeah.
expensive?
Yes.
Yes. It typically is. But you have to pay for a roof anyway. There is some added cost because you're adding the landscaping on it. They don't usually have any irrigation. They're planted with native plants natural to wherever they're located. So in San Diego and Southern California, because we are a desert climate, green roofs around here typically rely on succulents, which are cactus-like plants that they don't use a lot of, they don't need a lot of rain. But in Zion, no, this isn't Zion. It was in, that project's in North Carolina. They get a lot of rain here. So they have a lot more freedom of what plants they can put on the roof. They also started doing a lot of green roofs in urban environments, on skyscrapers in cities. I can pull together a whole bunch of pictures and maybe I'll put that at the end of one of our lectures sometimes, just to show you some examples. They can make roof gardens. You can have, you can grow produce in some green roofs. Sometimes they're just for aesthetics. You do have to be careful about waterproofing. You do need a fair amount of insulation. There's always a little bit of like a gutter or a water system at the edge, and they tend to have a fairly thick profile because it's building up lots of layers. You've got your plywood, your insulation, your water barrier, then your growing medium. It's not typically straight on dirt. It's more of a landscape planter soil that's mixed with vermiculite to keep the weight down. Sometimes you do have to beef up your structure a little bit more because it can get fairly heavy, especially since you're watering it. Or no, excuse me, you're not watering it. It is collecting rain and moisture, and it holds it in after it rains, before it disperses out. You can also combine them with active solar systems. You can have a green roof and then put solar panels on top of it. They do work well together. Did I answer your question?
Yes, of course. Thank you.
Okay, I think I probably gave you more information than you wanted to know.
Thank you.
Oh, if they're more expensive. Yes, they are, but in the right place, they are really awesome. Any other questions? Not yet. Okay. Back to the mouse. It's clear. Mouse drawing. Okay. So we talked a lot about some ratios, some performance, different materials for these passive systems in your thermal mass. The technical side of the material is based on two parts of what that thermal mass is, and combining them together gives what's called the heat storage performance, or HSP. It's where you're looking at the conductivity of the material and the heat capacity. Conductivity, as we know, is the opposite of resistance, or R value. It is how well that material is going to conduct heat from one side to the other. Water is an excellent conductor. So is concrete, brick, adobe. Wood, not so much, and air, not at all. As you recall, air is the #1 performing insulation material. So that is why it is very low in conductivity. So air is a very poor conductor, and that's why it's used for insulation as well as for creating a thermal break between surfaces. And that's also part of why wood isn't good conductor. Wood is cellulose. It's made up of lots of cells and there's a lot of airspace in between all of the wood fibers. So it's not a very solid material once you start looking at its substructure. So it does not conduct very well, although it does have a higher heat capacity. So heat capacity is based on the chemical nature of the material. Sometimes it's the heat capacity also can be referred to as thermal mass. So when we're talking about thermal mass in a passive system, that's talking about how well a material will hold heat. But remember, and that's why there's the heat storage performance factor, is that it's not just how well it holds heat. It's not just about the thermal mass, but it's also a factor of its conductivity, and especially in a tram wall, because you want that heat to migrate through your surface. Little less so in a direct gain system where it's just going to be absorbing the heat and it's based on surface area. You do need some thickness to it, but say for concrete floor, a 4 or 6 inch concrete floor is enough to be a thermal mass, versus a tram wall, you need more like 10 inches. So just a definition to understand is the heat storage performance is based on both heat capacity and conductivity of the material. So that's the last little technical part on passive systems. I'd like to share with you a modern hybrid system that is not super popular in the United States. It's a lot more popular in Europe right now. But this is a system that I was involved with installing in a project a couple of years ago. And what it does, it's similar to a radiant ceiling panel, or shoot, I'm blanking on the name. It'll come back to me. But it relies, so it's called a hybrid because it's not strictly passive. It needs either hot or cold water in a coil to help create the convection that will move either hot or cold air. So the energy aspect of it is in making the temperature of the water hot or cold, and the energy to run a pump. But it is a true gravity wall does not have a fan. Some I've seen have added fans to assist, but you don't need them. However, like any passive system, it's not a fast performing. It needs some time in order to let the natural convection of the air create the thermal comfort in the space. I kind of just went over this. So it's hybrid system. It relies on passive air movement. The buoyancy is of the air, that hot air will rise, cold air will fall. It does need heated or chilled water. So it can do both heating and cooling, which is pretty cool. It does take up a fair amount of space. You need a certain amount of width for your capacity of the system. Let me show you what this looks like. So it is a little fan coil, and a coil is it's like a radiator. It's a series of tubes that are all closely packed together where water will circulate through the series of tubes. If you think of like an old-fashioned radiator and smush it down and make the tubes a lot smaller, that's what a coil does. They're often called fan coils because when we get to active systems, when you combine it with a fan, that's the basis of modern HVAC equipment. But in this case, just the coil that either hot or cold water moves through. In the heating mode, or actually this diagram is cooling. So the coil is acting as a heat exchanger. And all that means is that it's transferring heat from the air to the water. And that can go in either direction. If the water is hot, it's going to make the air warm. If the water is cold, it's going to make the air cold. So in cooling, if you're running cold water through that coil with natural convection, it will pull in warm air. The air will pass over the coil and cool down as it passes over that chilled water in the coil, which makes it heavier, and the cold air will go down. You need a vent in and out. And as the cool air is moving out, it's going to pull more hot air in. And so it's a giant convection circle that as the air cools, it falls down. Then as it warms up, it gets pulled back in the top and falls over the coil again. So this is the passive aspect of this system. The opposite occurs in heating. When the water in the coil is hot, it's going to make the air hot. And so air will pass over the coil, heating up, and move into the space. The hot air will cool down in the open space and then be pulled in as it's cool, and the hot air is exiting out of the top. So this is relying a little bit on, or the convection is relying also on pressure, and that once you get that system going with the hot air rising and the cool air falling, it creates that natural convection, and it will be pulling the air around. So that's the section of it. This is just a picture of a coil mounted within a wall space. It has a drainage pan in the center because it will, because it can do cooling, it will create condensation, because as that air cools down, it's going to pull moisture out of the air. So you have to collect it, and then you have to drain it like a typical condensation in any air conditioner. Whoops, that's not what I wanted to do. The mouse. So that's generic pictures. This is a picture of the project where I was involved in installing them. So this one is a series of 3 different coils within this wall. This happens to be a half-height wall. And in this project, they wanted a more direct feeling in the space sometimes. So they did add in a fan to help assist the air movement. But we did this test, and what happens is when you turn the fan on, it makes the air move faster, and so it has less time to heat up or cool down. So without the fan, you get more temperature change from top to bottom than you do with the fan, because it's more gradual and the air moves more slowly across the coil, so it has more time for heat exchange. But a lot of people don't feel cool if they can't feel air blowing on them, which is why for an immediate assist, if the client in the space was feeling too uncomfortable, they wanted to be able to walk up and push a button and turn on a fan and have it blow cold air, even though they were going for this awesome passive system. So that's what it's like sometimes when you're trying to create truly sustainable projects. You have to work with the clients and all of their ins and outs and fears and appease. Sometimes it's appeasing multiple people in a household, or in a if it's a residence, or multiple levels of people in a commercial or business location. So, and you guys are all probably going like, who would do this and why is this? And this is like super crazy. Like I said, they do more in Europe. There's a couple different companies that make this type of product. And this is the project that I worked on where these were installed. This is up in Santa Monica. This is a Frank Gehry residence. And it had these giant glass boxes for the dining room and living room. And that's where this series of 3 of these, so each one's about a half a ton, so you get like 1.5 tons of capacity. This is in the living room, which is this glass box right here. Glass ceiling, glass walls with automated shades, automated windows, shades on the ceiling. There, lots of stuff going on. Super fun project to work on, incredibly challenging. So this is the front of the house that's facing out towards the beach, or towards the northwest in Santa Monica. This is the other side, looking at the other side of the house. So the beach is out beyond the house. This is the interior courtyard side. So super fun little project. Actually, it wasn't very little, and it lasted forever. And there were all sorts of problems, but at the end of the day, incredible learning experience. And learning what is possible, although sometimes keeping it simple, best way to go. Straightforward, passive heating, you got a window, you got a floor, you have an overhang, you do it right, I'll close the curtains at night, you're good to go. No fans, no hot or cold water, but it doesn't do cooling, so it's all a trade-off. Particularly like this picture, I took it one day when I was leaving the site, just at sunset was happening. Makes me appreciate living in Southern California. Okay, I wasn't sure how long that was all going to take. I have a couple more cool projects I want to show you guys, but just because I didn't want to run out of time, I wanted to know if anyone had any questions regarding the assignment that's due today.
I do.
Okay.
I'm wondering about number 9. Which is the most important and why?
Where is number 9?
Those acronyms.
Oh, number 8. Oh.
Yeah, so it's number 9, but you're basically looking at number 8. It asks which of those 4 acronyms are the most important.
Oh, is that on a second page? I totally didn't do that on purpose. Try to.
Yeah, it's on a second page. Yeah,
oh,
there's more.
Well, that was bad printing on my part. Oh, there's a second page to this whole thing?
Yes.
Whoops, I forgot to add that in here. Let me just open that up real quick. It'll only take a second.
Your thing.
Page 2. Okay, yeah, from number 8. Which one is most important? Okay. So SHG is solar heat gain. SHGF, solar heat gain factor.
Right.
SC, solar coefficient. SHGC, solar heat gain coefficient. Okay, in terms of what's important, you're right, that is a really good question, and I think maybe I was perhaps a little bit vague, or maybe I missed that point when I was giving a lecture. The most important thing that's going to affect you guys or us as architects is the solar heat gain coefficient.
Okay.
That is directly related to the windows that we have to specify to go
Okay.
into our projects.
That's what I ended up with.
Okay. The other three terms reply to understanding different performance. No, that's not right. How do I explain it? There are different definitions within the building envelope. How, but you're never going to need to use them as a designer. You need to know them because this is a class you need to take. But most important thing is the solar heat gain coefficient, which has to deal with windows, because that's what that's the value you're going to be looking at when you're working with your mechanical engineer on how well your glazing is performing. So I'm going to make a note of that on the wording for that question for future generations.
Thank you.
I learned so much from you guys too. Okay, any other questions on the assignments?
Yeah, I have a question. Can you hear me?
Yes.
So for number 7, a heat load is heating load is the heat loss, correct? So if a latent load I found it's an instantaneous cooling load, but I didn't know how to like I was defining it, but I wasn't sure how to explain it, and maybe it's just that I'm not getting the concept to it, or okay. I mean, I know you've gone over it, but
right. So so heating load is only changing the temperature of the air. It is not affecting the moisture content in the air. Heating is dry heat. Okay, let's see. It's just changing the dry air temperature by adding heat into a space. It is again, I think you're right. That's probably not a well-worded question. Number 7. Because it's a dry heat. I know that's probably not explaining it very well. I think the reason I put down the question was to emphasize that heating is only sensible heat, and cooling is both sensible and latent heat. Cooling is always includes removing that moisture from the air that's given off by people breathing in the space, in addition to the radiation coming off of our bodies. That's an additional load in addition to the air temperature being hotter and trying to remove some of that heat out of the space. It's also directly tied to that concept that hotter air can hold more moisture, colder air holds less moisture. And part of the cooling process is to remove moisture from the air. That is that's key, because if you're not removing that moisture, you're going to end up with cold, saturated, moisture saturated air that's going to be uncomfortable and is also likely to condense and create condensation. So it's the purpose behind the question is to emphasize the difference between the two. And I will work on rewarding that to make it clearer for future generations.
Okay, all right.
I'm glad you asked. These things really help me know, because I sit here in my head and write down questions, and I think I'm being clear, but I'm not always. So I appreciate the feedback. Any other questions? No. You guys are still awake Friday afternoon, hanging in there a little bit? Okay, I have a few more minutes. I'm going to go back and I want to show you two more really cool building projects. This is showing that buildings is the best way to, I think, to help you guys expand on the possibilities of what you can do. This is a evaporative cooling technique called a shower tower. This is a building in Australia. It's called CH2. I think it's in Melbourne. And again, this building has many, many different techniques on it, but this is just one. This is an evaporative cooling technique. So it fits in with, it's a almost passive. I guess I could call it another hybrid system because it does include the moving of water. So there is a pump in there. But again, it's relying on natural air movement to create the cooling. So this is a passive cooling strategy. So it's a shower tower. It is like the name says. You start off with an injection of water in the form of moisture at the top of a vertical component that as that moisture is falling down, it is cooling down the air, and the cold air will fall and be pulled out of the bottom, which will then pull hot air in at the top, which will pass over the water and become the dry air will pass over the water and cool down, and then so that little convection cycle is occurring. Again, evaporative cooling, so this works well in dry, hot climates. Would not work well in a really moist, like Miami or Florida, which is strange that sometimes they call evaporative coolers swamp coolers because you can't actually use them in a swamp. I never understood that, but maybe it's because they make it feel like a swamp because you're adding moisture to the air. That could be, I don't know. I don't know the origins of that word. But this is a section through the whole building where they have multiple different techniques going on. So they've got the shower tower on the north side over here, pulling down cool air. It collects the water at the bottom. It gets pumped back up. There's also a wind turbine, and that's combined with a ventilation shaft. So the red arrows are air being pulled out of the space and up out of the building through this shaft. There's this really cool shading system on the outside of the building. Let me show you a picture of it. So it's got all of these vertical shades on this facade here that are movable. So this image here is showing them open on the far right. The other two facades, they're a little bit more closed. You can see the shower towers over here on this side of the facade. We got the wind turbines going on up there. the top of that, those vent shafts coming out of the building. It's just a really, really cool project. Let's see what else it has going on here. It's got solar, active solar panels, thermal mass in the floor, displacement air. That's a type of active cooling system where instead of having large grates that blow more volume of air, it's a much more subtle system with many more smaller distribution air coming up through the floor. Chilled beams. This is similar to the gravity wall concept, where it's running cold water through in a tube through a piece typically in concrete in the ceiling, and they're designed, and there's regulations on, or there's guidelines on how much airspace you need around them to allow for the natural convection of the air, so that as the hot air goes over the chilled beam, it will cool down and fall, and that will create that circulation and convection of the air. You have to have fairly large open floor plates for a chilled beam system to work. They don't work when they're really small very well. Oftentimes they'll be in classrooms or laboratories or large spaces that have big open floor plates. Says the north facade is green. I don't have a good picture of that, unfortunately. Can't really see that. This is the north side's around here. Oh well, I'll have to look for another picture of that. Okay, the second cool building I want to show you. Has anyone seen this project before? This is a DPR's offices in Phoenix. Okay, DPR is a construction general contracting company. This is so cool. So this is an adaptive reuse building. Here's a picture of it on the upper right-hand side. This used to be an adult bookstore on this like strip mall in Phoenix, and this construction company bought it, completely renovated the building, put in this super cool sustainable project, and it just looks awesome. It also has the passive shower tower concept. They call it passive cooling towers here. Again, where they're using moisture to cool down the air. They've combined it with direct ventilation going into the building. So as the cool air cools down, it can flow into the building. They've got I think this is solar here, and sort of a green wall creating this green space. That's what this space here is in the bottom picture. These black tubes are the passive cooling towers. Let's see. They've got a lot of natural daylighting going on. They've got a solar chimney for natural ventilation. And so they're using the south side here to cool down the water, have it circulate through the space, and then exhaust and out through their solar chimney, which in the picture is this thing up here, and it runs the length of the building in that direction, matching the section. So just a really interesting building, using a bunch of different techniques. I believe this is a complete net zero project. They've got their active solar array over the parking lot. Here's where they're stating their U factor and their SHGC. These are incredibly good performing windows with also a high light transmittance, visible light transmittance for clarity and being able to see. Yeah, I just find it super inspirational. DPR also has a really good project here in San Diego. It's not to this degree. I don't think it's complete net zero, but they do a lot of really good methods too. If you ever get a chance to go to an event, I know the San Diego Green Building Council sometimes has an event or a talk, or they have a big classroom there that they let different organizations have programs there throughout the year. So you can, they have, there's classes and stuff that you might get an opportunity to go see their local building. It's up off of the, just north of the 52 off of the 805 in that industrial complex there. I don't know, the Prometrics used to be up there, the place you have to go take all your architectural exams. I don't know if they're still, if that's still there or not, but that's where the office is. And overall as a company, DPR is a really good rep for doing a lot of good sustainable work. So fun, inspirational buildings. And it's Friday, 4 o'clock. You guys ready to move on to your weekend? Thumbs up? Okay, me too. I'm ready. There you go, Mars. All right, guys, don't forget to turn in your assignments today. And we're moving on with natural ventilation on Tuesday. And we'll have a new assignment on Tuesday too. All right. Any questions? Last minute questions? Nothing? All right, guys, let's stop recording.
Thank you. Have a good afternoon.
Have a good weekend. Bye.
Thank you very much. You guys
Thank you.
too.
Bye.
Bye. See you next week.